So, good afternoon to all of you. Today, we want to discuss local compactness, which we started in the last lecture. So, in last lecture, we defined what is the locally compact spaces. A topological space X is locally compact at a particular point small x if there exists a compact set C and an open set V such that X belongs to V, which is a subset of C. So if for every point x we can find this pair of v and c around the point x, then that for each x satisfies this property, then the whole space is called the locally compact space. So this is basically the local behavior. Related to local behavior, this property is defined, and we have seen the examples that if every compact space is automatically locally compact space, and we have seen that R is locally compact. In general, Rn is also locally compact. So here we consider R. So we discuss the intervals, and around every x we can find a neighborhood of length 1 that is open set V, and its closure is the compact set. The same way, if we take for example in R2, we can consider the neighborhood around the point x of radius 1, and its closure we can take. So that will give the proof that Rn is also R2, and in general Rn is also locally compact space. And even in more general sense, every matrix space is a locally compact space because we can define the ball and neighborhood in the matrix space also. But there, the uh, so what we want to discuss is one point compactification. So we know that R, R2, Rn are locally compact spaces, but they are not compact. So how to make it compact? By making it a bit larger set. So the idea is, even we add single point, that itself will make that space into locally compact space. So by just adding up one point, we can make R, R2, Rn into compact spaces. So that is this procedure. So this stereographic projection we already know, but we want to do that in general case for example for Rn. So for that, what we do is we start with any locally compact space, locally compact Hausdorff space X. So in particular, we can take throughout X equal to Rn, for example. So if we take X equal to Rn, then we can define Y, which is Rn union one point, which we call infinity. We are denoting infinity. So that point infinity is not like infinity in the real line. So in real line, infinity we take, which is limit of 1 to n, those numbers, right? So but here it is not like that. This infinity is just any point which we are adding to this particular set x. So with by adding this point, we will get another set which is capital Y, and on Y we can define a topology. So that collection will consist of all open subsets of X, and it will also contain the subsets of the form Y minus C, where C is a compact subset of X. So this new collection tau infinity will contains either type 1 sets that are basically open subsets of X, and type 2 set, which is a set of the form Y minus C. So what is Y? Y is X union infinity minus the set C, where C is compact subset of X. So this tau infinity is a collection of subsets of Y now, and so therefore we can ask the question that whether tau infinity itself is a topology. So it satisfies the axioms of topology. So we started with verifying those axioms in the last lecture. So first we verified phi belongs to tau infinity, y belongs to tau infinity, and then we have seen that The second property is that it is closed under finite intersection. In particular, if we take any two sets from this type 1 type 2, then intersection of those two sets also belongs to tau infinity. So that we have verified, and then we were verifying the third step, that is tau infinity is closed under arbitrary union. So for arbitrary union, we started with one particular collection of uh, arbitrary ele elements of tau infinity. So there are three cases. Each u alpha belongs to each u alpha is of type 1, or each u alpha is of type 2, or some are of type 1 and some are other type. So first we verified, suppose each of u alpha is in tau x, that means each u alpha is open in x. So in that case we already know that tau x is a topology, so union will also will be open in x, and therefore it belongs to tau infinity. So second case, we have observed that uh, each collection this is of the form second type, that is y minus c beta. So in that case, if we take the union of those y minus c beta, then it will be nothing but the complement of intersection of c beta. And uh, since each c beta is a compact set, uh, it compact subset of x, so its arbitrary intersection is also compact. So this result we have not discussed in general, but at least we know that that holds in Rn. And finally, every union of the mixed type, so some of the sets are of the first type and some of the sets are of the second type. So if we have such a union, then that union we can write as a by taking complement we can simplify, and we will basically get a set of this form, y minus c union u. So now our only thing we need to check is that this element belongs to tau infinity. So that is our claim. So to verify this now, we will use the Venn diagram again. So suppose I have a set X which is compact Hausdorff space, and if I add infinity in that, then I will get the space Y. So in this case, uh, if we have compact set C, and if we have a neighborhood U, then what will be this particular set Y minus C union U, right? Because we want to see what will be this set Y minus C union U. So if you observe, this is nothing but the uh, from Y we are removing the points of C, and we are adding the points of U. So this will be basically this, all the points, right? All the points will be there. So this, except this particular part, right? So so this set we can rewrite using set theory as Y minus C minus U. So we can see this again, that if I remove U from C, then we will get exactly the part which is left here, right? So this is exactly this part, and that we are removing from Y, so we will exactly get the same set. So these two are equal, and once these two are equal, we want to show that this belongs to tau infinity. So this belongs to tau infinity means either it is of the type 1 or it is of type 2. So we actually show that this is actually uh, of type 1. It is open subset of X. So to show that, what we will do is note that the set C minus U is nothing but C intersection complement of U in X. So first we have to observe this, that C minus U, when we take the complement of U in C, so uh, no, C minus U is exactly this set, and that set is nothing but uh, the points of C which are also in the complement of U, right? So point of C which are basically not in U. So now what we'll get is, we know that U is open, so its complement is closed, and right. So X minus U is closed because U is open in X. So this is closed subset of closed subset in X, and then what we know is that uh, the C minus U, which is intersection of C with this closed set, so therefore it is C intersection X minus U, which is nothing but C minus U, is closed uh, closed subset of C. So what we know is that C is a compact space, right? We already discussed this, that C is compact space, and every compact subset of Hausdorff space is always closed. So C is closed, and X minus U is also closed. So intersection of two closed set is closed. So we can write here, because C is closed. So therefore intersection is closed subset of C, and what is C? C is compact. So now we have a compact closed subset of a compact space, and therefore it is also compact. So therefore C minus U is also compact. So why it is compact? Because C minus U is closed subset of compact set C, right? So closed subset of compact space is compact. So C minus U is compact, and once it is compact, therefore Y minus compact set belongs to tau infinity, right? So this is actually of type 2, that a set is belongs to tau infinity if it is type 2, if it is Y minus some compact set. So this claim we have proved that this set Y minus C union U, which is nothing but this particular set, which is element of tau infinity, right? So therefore we prove the claim. So this will finally prove that tau infinity is a topology. On Y. So now we have proved that if we start with a locally compact space X, right, and on this locally compact space, if we define this, if we consider y, which is x union the point infinity, then on that set we have defined tau infinity, which is a topology. The question is that since our x is locally compact and Hausdorff, whether y is locally compact and Hausdorff with respect to this topology tau infinity. So that is the next question. So and another question is that whether this topology is the subspace topology. Uh, so let us start with first the next question, that is tau x a subspace topology. So actually we are going to prove that it is a subspace topology. Tau x is a subspace topology. So actually what we want to prove here is that since x is a subset of y, so tau x is nothing but the intersection of open set of y intersection x. So this we want to prove. So that will give us that tau x is the subspace topology corresponding to tau infinity. So one of the inclusion is trivial. So other one we will prove now. So we will show that this is a subset of tau x. So let us start. So what are the sets here? We know that the elements of tau infinity is of two types, type 1 and type 2. So let us start with the type 1. So if I have the set in T infinity, which is uh, which is of type 1, that means it is in tau x, then then what we take, if we start with the element of tau x itself, then that element is nothing but v intersection x is nothing but v itself, right? So uh, what we have written is that if I take any element of tau x, then its intersection with x is v, and v is, we already know it is in tau x, right? So what we proved here is that tau infinity intersection tau x is a subset of tau x. So if I take first type set, that it is already in tau x. Now we'll take the second type set. So if I take v is of the form intersect the complement of the compact set. So if we take complement of the compact set, where C is a compact subset of X. So this is the second type set in T infinity. Now we want to show V intersection X is in tau X. So that is what we want to show. So if we take V intersection X, then it is nothing but the complement of C in X, right? So this we can observe, and so because what we know is that we have the space X, Y, what difference is only infinity, and C is actually a subset of X. So therefore the complement of C in Y and complement of C in X is same, right? When we take the intersection. So V intersection is X minus V intersection X is X minus C, and then X minus C is in tau X. Why? Because when we take C is a compact set, of the Hausdorff space. So C is closed, and once again this we are using that C is closed, then X minus C is open. Is open in X, so that means basically it is in tau X. Right. So this will give the second type sets when we take its intersection with X, then that is also in tau X. So that means we have proved that whether we take any set which is element of tau infinity, either type 1 or type 2, it is always contained in tau X. It is always an element of tau X. And then the converse is anyway true, that we have already seen in the type 1 case, that conversely if we take any element of tau X, then V intersection X is V itself. So it is anyway in this collection. Right. So what this means is that so in this case V intersection X is so every element of tau X is here basically. So the converse is also true. So finally we get tau X is equals to V intersection X, where V belongs to tau infinity. So that is just observation that tau X is basically the subspace topology. And then the next claim is that Y is compact with respect to this topology. So to prove that Y is compact, we start with open cover. So let C be an open cover of Y, right? So if we start with open cover of Y, and then uh, since we have a open cover means each element of C is element of tau infinity, it is open with respect to the topology tau infinity, and we know that uh, infinity is element of Y. So there exists some element of this cover which 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 consists infinity, which contains infinity, right? So there exists an element of tau infinity such that infinity belongs to infinity belongs to V. Since it is open cover, it contains, every point is contained in at least one open set. So now this open set contains infinity. So that open set cannot be of type 1 because type 1 sets are basically open subsets in X. So they never contain infinity point. So therefore V is of the form Y minus some compact set. Uh, where C is a compact set in X, right? So this is this is what we get from this, that if V contains the point infinity, then the open set which contains this particular point is of this form, and then so basically we have open set which contains all points of Y minus C. So now we need the open set which covers the points of C, because we want to cover the Y by finitely many open sets. So now since C is a subset of Y, and therefore we have the cover of Y, which is we denote it by C, right? So C covers Y, and C is a subset of Y, so therefore C covers this compact set C, right? So family C covers the compact set C, and since it is an open cover, so I think we mentioned that C is a open cover of Y, so C is open cover of C. So since C is compact and this collection C is open cover of the set C, C as a finite subcover. So let us say that this subcover has consisting of the sets U1, U2 up to UN. All are the uh, elements of C, right? So this compact set C is covered by U1, U2, UN, and the complement of C is basically V, right? So that means this both we combine this all sets, therefore V comma U1 U2 UN covers the entire space Y. So using the open set which contains the point infinity, we get the compact set, and then for that compact set we get a finite subcover. So using this finite subcover and that open set, that will give the entire finite cover of the Y. So therefore Y is compact, because every open cover of Y we can find a finite subcover. So last thing related to this we want to prove is that Y is Hausdorff. So Hausdorff space means I have 2 points which I can differentiate by the disjoint open sets. So that is meaning of the Hausdorff space. So let us start with 2 points x and y in capital Y. So if these both points are in X, so what is the difference between capital X and capital Y? Capital Y contains the point infinity, which is not in capital X. So if I choose these 2 points X and Y, which are basically different points, then there are two choices: either both X and Y belongs to capital X, or one X belongs to capital X, then Y belongs to Y is outside X. So that means basically Y is infinity, right? So that will give us two cases. So first case is that if X comma Y belongs to X, in that case we already know that then using X's Hausdorff, we get two open set in tau X, which is subset of tau infinity. So that means they are also open in tau infinity, such that X is in U and Y is in V, and they are disjoint. U intersection V is null set. So basically these two sets U and V, which are open in X, they are also open in infinity. So therefore it gives the required U and V for Y, for tau infinity. So in this case it is trivial, but the other case needs argument. So other case is that if my one point is in X right? And the other point is infinity. So in this case, we will use we will not use the X is Hausdorff. We will use X is locally compact. So using X is locally compact. So this is a place where we are actually using the locally compactness after we have defined. I think we have not used this property, so we are using it here. So since X is locally compact, so what is the definition gives? Definition gives that I can find V, open set V, and compact set C such that X belongs to V subset of C. So here also we'll get that. So since X is locally compact, there exists a compact set, say C, and a neighborhood U such that X is a subset of U, X belongs to U, and which is subset of C, right? So this is what we get using locally compactness at the point X. So now what we need, we got one open set, but to show Hausdorff we need another open set. For that we use this compact set. So what we do is we will consider the open set V, which is the complement of C, right? Where C is compact in X. So since once again C is a compact subset of Hausdorff space, it is closed, so its complement is open. So therefore V is open, right? Uh, and then since V is open, uh, then X belongs to U, infinity belongs to V, and U and V are open in tau infinity because U is open in X, so it is also open in it is element of tau infinity. And the final thing will also follow, that is U intersection V. So what is this? This is U intersection uh, complement of C, and that is null set because of this criteria, right? So that is we are using this here, that U intersection Y minus C is null set because U is a subset of C, right? So we get U intersection V is null set, and we got the elements containing X and Y. So finally this will give us that Y is Hausdorff space, topological space. So this will prove that this one point compactification. So we can summarize that if I have a locally compact space X, and I have a which is compact locally compact Hausdorff space X, and we add a point infinity in that, we construct a bigger set capital Y on which we define the topology tau infinity. Then tau infinity is compact. Tau infinity is also Y is also compact Hausdorff space with respect to tau infinity. So original space was locally compact, but now we have a capital Y which is a compact space. Okay, so let me stop here.